All right, welcome to part two of hybrid transmission operation theory and diagnosis. We left off on a video that I normally show in class of an operation of the Prius transaxle complements of Weber, but we couldn't do that here on this particular narration. But I am going to link the video directly from YouTube from Weber Auto, and it'll be on your Canvas page. So let's get going on the construction. So this is a Toyota typical transaxle assembly, either chain or direct gear mesh. The chain is an older style, MG2, Generation 2. Here's your Gen 3 gear-on-gear style. But you still have MG1 right here, MG2 there. Now notice MG1 stator looks different. They did it for an upgrade for efficiency, and they also added a secondary planetary gear. But basically, it's a real simple transaxle, not many moving pieces. So anyway, but all this stuff creates heat. So in order to cool it, here is your transaxle assembly. Here's your inverter assembly. You're going to have basically the motor electronic cooling system, which goes through the inverter and transaxle, a little electric water pump. Here's your overflow, and all this coolant's being pushed through a heat exchanger, which is either part of the radiator or a separate piece up front there. It could be the lower half of the ICE radiator. So if you remove a radiator, it's got 4 hoses on it. The top half could be for the ICE, the engine. The bottom half could be the motor electronic cooling section, which is the inverter, transaxle, this pump, this reservoir. A good tip that I use when checking for this, make sure it works, as soon as this vehicle is ready, the ready light's on, you should have turbulence in this reservoir that goes to the inverter. Because as soon as it's ready, it's creating heat, and it needs to get it cooled, so the electric motor turns on, circulates coolant, and you'll see that turbulence up here. So if you have a system that's overheating, and a DTC that says overheating, and you look at that reservoir with the key or the vehicle in the ready mode and there's no turbulence, you don't hear this fan or the water pump turning on, you want to diagnose accordingly. Checking for powers and grounds, make sure this is working. Oil pump may be driven by an electric 12-volt brushless motor, by the ICE, the oil pump driveshaft, check manufacturer specifications. This one's driven by the ICE on the Toyota, but basically it's going to help lubricate lubricate this transmission or keep the vehicle in gear when you come to a stop or the ICE turns off. It depends on the vehicle, but there is a secondary oil pump in some of these transmissions, so just be aware of that. Here's your construction of the MG2 stator. You look at this one pulling out of this transaxle housing right here. There's your temp sensor right there, tell the computer the temperature of the MG2. This elliptical ring right here, that's part of the encoder resolver to let you know the position of that rotor. This is the rotor sitting right there in MG2. There's that union right there of the Y wound, and then there's that temp sensor right there. Comes out the transaxle there. Service procedures performed at specified intervals and include draining and filling both the oil and coolant. There are service plugs both at the bottom of the transaxle. And coolant's filled using either an airlift tool, scan tool to operate those electric motors, remove air pockets, or just a simple drain and fill. It depends on the manufacturer. I recommend getting used to your service procedure within Mitchell or ALLDATA, whatever your shop's using. So, and again, the transaxle oil is filled through a fill plug to a specified level. Think like differential or manual gearbox. Pretty similar. Some do have a dipstick, but pretty much all of them are going to be off. You're going to check them when the off vehicle's not running mode. So make sure you're using the correct fluid. I don't believe in universal fluids. I also am cautious about flush machines because there can be contamination. Some transaxles are highly, highly picky for the correct fluid. So use the OE fluid. As far as the Ford ECVT transaxles, they're very similar to Toyota Power Split. So once you learn a Toyota, you can learn many other manufacturers. They basically pay to use this system. So you'll see this on Nissans as well. But the electric motors are on different axes. Where the Toyota, they were linear. The Ford will have them kind of offset. So you'll see that here in a second. And also the inverter control module is part of the transaxle, so it's replaced as a unit, unfortunately. Kind of like those combo DVD VCRs. If one goes out, well, you got to get it all. So allows a more compact transaxle, more efficient cooling, minimal voltage loss, but that can come at an expense to the consumer. So here's the Ford setup. You notice it still has the big giant traction motor. Toyota calls it MG2. Ford calls it a traction motor. What Toyota calls an MG1, Ford calls a generator motor. So just different nomenclature, but same thing. And then up here is your capacitor, inverter, integrated power unit, all built into this transaxle assembly. Here's a picture of the case. You know, the ICE couples right here. Here's your inverter, capacitors, etc. Coolant tubes and lines. And again, those MG1, MG2, or generator traction motors, they're stacked on the Ford versus linear on an axis like in a Toyota. But diagnosing them is basically the same. Here's an actual picture of that. MG2, or what Ford calls a traction motor, and then MG1, that generator comes off the back of the ICE right there. And here's your final drive. All this is your inverter, just like on the Toyota had it up top, but in the Ford, it's part of the transaxle. So again, this can change. New model years, keep up to date with your manufacturer you're working with or on. So read your service manuals. If you get bored, read a new one and get comfortable with new technology. Because again, what I'm telling you now can be wrong tomorrow. It could be wrong today. Don't trust me. Anyway, moving on. So Honda IMA, remember that Civic we had on the rack there at the shop? Their hybrids, at least in the IMA and the early Honda hybrids transmissions, they use one that's similar to their conventional vehicles, CVT design. IMA is a sandwich unit between a traditional ICE and traditional transmission anyway, so it made it quite easy for them to use this type of system. Okay, no planetary gears on this one. Like the GM2 mode, there's an electric pump to keep the transmission from shifting into neutral during idle stop. What that means is when you come to a stop and the ICE turns off, if the transmission relied on the ICE running, the ICE powered that transmission pump, it could shift into neutral when it loses pressure. So they have an electric pump to keep it from shifting into neutral during idle stop. And then as we know, ICE runs most efficient in narrow power RPM range, like we discussed earlier. This is why transmission have gears to control the RPM. But Honda doesn't use gears. They use this CVT. So here's your steel belt system right here. I'm not going to go into too much of this detail, but basically it's going to change these pulley sizes, which is going to change the size of the drive and the driven respectively, and that changes the output. So CVT transmissions kind of have a weird feeling if you're not used to it. They don't have that stepped, geared feeling. They just kind of change ratio as you drive along. So the ICE will get to its operating RPM that's desired, and it just kind of stays there. It's an odd feeling. Some customers don't like it. I remember working for Ford when the Escape used this type of transmission. People complained on the hybrids that this feeling, they thought it was slipping, or they thought it wasn't shifting, or etc. Here's another cutaway view of that Honda CVT, and it shows these two-piece pulley. As it moves in and out, it's going to change the diameter of the pulley from drive to driven. So there it is again. What's interesting is these belts push rather than pull. Like on your serpentine belt, they pull. These ones push. The big pieces of steel in between here. And this transmission uses a very specific fluid, and it's prone to failure with contamination. So be careful. Here's another picture of those pulleys as they change size. They kind of squeeze in together or move apart. Here's one that's showing you as it moves apart, that belt drops down further. As it moves in, it goes up. This changes that diameter from the drive to the driven. I talked about the steel belt pushing. So there's only 3 clutch packs and 1 planetary gear in this design. Basically, you have this clutch pack up here, here, and here, right there, the start clutch. So park neutral, no hydraulic pressure is applied to any clutch, resulting in no torque applied to drive, pulley, or shaft. Whenever following components are replaced or removed, the start clutch must be calibrated. So think about when you're disconnecting the battery, backup fuse, TCM, transmission assembly, lower valve body, or engine assembly. You're going to have to want to go through the start clutch calibration, or you'll have either an operative car or customer complaints. It's the law. Like I mentioned earlier, these transmissions are highly susceptible to contamination, so make sure you use the correct manufacturer oil. I wouldn't buy this whole universal thing, but that's just my opinion. A lowly shop teacher. So diagnosing motor generator faults basically fall into one of 3 categories. Inoperative, noise, vibration, and overheating. Of course, these can be elaborated into much more detail, but as a general rule of thumb, you're going to get complaints that say, hey, it don't work, it's making a noise or vibrating, or it's overheating. So always check fluid levels, scan for DTCs, and test drive the vehicle if possible. My recommendation, any car that comes in, I'm checking fluid levels, scanning for DTCs, and test driving the vehicle. I'm going to check, do a quick shakedown. Is it safe to drive? This is all stuff to kind of cover my butt and make sure I don't get hurt. So I'm checking for DTCs when they show up, so no one blames anything on me. I'm checking fluid levels because I'm the professional. If I drive a car with low fluid and something breaks, guess whose fault it is? Yep, yours. Also, I'm not test driving a vehicle that I don't think is safe, so I'll crawl underneath it at least and look. Does it look safe? Does it have the appearance of being maintained, etc.? This also helps me in my diagnostic process. Something to think about. So some DTCs provide subcodes like this P0AA6-612. The -612 is your subcode or INF or info code, they're known as. This is going to give you maybe a little enhanced data on that DTC. Might help you pinpoint it a little bit better. So like an AA6 means high voltage system isolation fault. Subcode 612 says the insulation fault is in the transaxle area. Although this DTC does not tell you what's wrong, it may kind of points its finger and nudges you in the right direction to help you out. Here's a graph showing you that. So here's the different INF codes down the center and the detailed information on the right, all giving you more enhanced data on that general P0AA6 hybrid battery voltage system isolation fault. Basically means something's shorted. You need to go find out where. In this situation, I would isolate the different sections of the car and then use a megameter isolation meter to determine where that fault is. I have attached a separate video that you can watch on how to use that megameter tool. But you can use that not only with the stators, with all the high voltage cables. You just have to remember to isolate each section you're testing so you know where the fault is. Visually inspect for damage or aftermarket modifications. This applies to not just hybrids, and this is in general. Again, like I mentioned earlier, before I test drive a vehicle, I'm checking fluids, etc. I'm giving a good visual inspection for safety and looking for damage, aftermarket parts. Does this person modify stuff? Was something recently added? All of this is going to help speed my diagnostic process. Okay, so familiarize yourself with the components and how the system works. How are you going to fix something if you don't know how it works? So you got to know what's normal in order to know what's not. Before diagnosing anything, I also review service info, check on recalls, TSBs, follow a logical diagnostic process. So I'm just I'm explaining to you my process that worked for me for years. I'm not trying to reinvent the wheel. If there's a recall or a TSB, by all means, I'm reading it, I'm doing it, moving on to the next car. So all of this can be done pretty quick. Once you get the system down, the visual of the system, visually inspect, there we go. Familiarize yourself, trying to visualize all of it in once. And then check recalls, TSBs, fluid levels, all that can be done in 5-10 minutes, super quick and really helpful. I also check, again, batteries, make sure it's fully charged, all my fuses if I'm doing an electrical test. These are things that I did in a habit just to help pinpoint. And then I would follow a hunch for 5 or 10 minutes, but then I'd make sure I gave myself a time limit, that way I can back off and do the actual diagnostic procedure if my hunch wasn't there. So let's say there's no TSBs or recalls. Your pinpoint tests have told you to remove the transaxle for further testing, but are you sure? It's expensive and hard to remove, and it would be a bummer to take it out and it's not the problem. So what do we follow as tests? That's right, trouble tree charts. And my favorite trouble tree chart. Does it move? No. Should it? Yes. WD-40. Does it move? Yes. Should it? No. Duct tape. Otherwise, no problem. Now, joking aside, follow your trouble tree charts, your power flow, or your diagnostic charts, the flow, because it's going to be, it's kind of designed as a catch-all. So do what I mentioned earlier first. You create your own system, go off hunches, but if you're kind of up the creek and you're still kind of, I don't know what's going on, you can follow that trouble tree chart and it's going to give you kind of a catch-all. They're not meant for speed. They're just meant to catch everything. Are they perfect? No. But it's going to give you a good rule of thumb. But if you know how the system works and you take that magic away, like I emphasize in class, where I'm trying to show you the physics behind how everything works, if you understand the physics, the theory, then when you read these charts, it's gonna jump out to you. You're gonna see the problem more times than not. So again, that's why I'm so heavy into the trouble tree stuff. So this basically is going to conclude part 2. We're going to bring in part 3, but before I do, I want to ask you to go ahead and look at, there's another video in there of what a car sounds like with an ignition misfire. I want you to think about what you think is wrong, and then part 3, I'm going to tell you what the complaint was caused by. All right, thanks for watching.